Now for SDS page. Your gel polymerization and structure are basically the exact same as in a native page. What makes SDS page different is what we're going to talk about on our next slide. So the process for developing and running an SDS page is basically the exact same as that of a native page. One major difference in terms of the name is SDS stands for sodium dodecyl sulfate. But page still stands for polyacrylamide gel electrophoresis. Okay, now that SDS dissolves hydrophobic regions of the protein and breaks non-covalent ionic bonds. Okay, so what this is going to do, what the SDS is going to do, is basically take a protein from this globular shape right here to something that looks like this. You know, it still has some shape, but in terms of it being packed really well together, it no longer does. I like to think about it as my fist right now is a native protein. Now, when SDS is present, here's what it looks like. One of the things that I like to draw your attention to is my fingers are still kind of, they're very close to one another, okay? So there are forces that are still holding my fingers next to one another. So SDS goes from this to this, or that. Okay, so that is, the name is going to be one factor that's different. Next is the sample buffer. You're not using the native sample buffer. Instead, this is commonly known as the lamellae sample buffer, or if you go to Bio-Rad or some other vendor's webpage, you'll find it likely labeled as the SDS sample buffer. Now, what this sample buffer has are a couple of things. It's got glycerol for density, so that it can pull down a sample in a well before you turn the electric field on. It's got a dye, so you can visualize as the proteins migrate through the gel. Then it also has, well, a pair of reducing agents. And these two reducing agents are maybe the most important part of this all. They are beta-mercaptoethanol also known as BME, and our other reducing agent is DTT, also known as dithiothiotol. Now, what these two different reducing agents do in terms of the overall protein structure is they are going to, well, in practice, they're going to stink. They smell bad. What they are also going to do, in addition to smelling, is they are going to break disulfide bonds. So we're going to be breaking those disulfide bonds, and so what's going to happen is this protein right here, it's going to go, the SDS is going to cause it to go from that globular to that shape, and then from here it's going to go to something that's like that, linear. Okay, so that means all of the charges, all of the positively charged and negatively charged residues are exposed to the environment. Okay, now in addition to that, what's not presented here in this model, I'm going to call this model A, what we need to think about is model B. Okay, so we've got something that looks like this. And whenever we add we have the SDS, which is in SDS is also in this lamellae buffer, or in this SDS page sample buffer. Well, what's going to happen is we've got something that looks like this. Okay, so we got those two things. Now, if we just added SDS, we'd see definitely something that looks different because, well, it's a little bit more linear. It's not that globular thing. It's not that the packed together thing. But then when we add the DTT and BME, lo and behold, we get this. How? Why? Well, none of the reagents that we added had any sort of proteolytic activity, so we didn't have to worry about them breaking any sort of peptide bonds. But maybe what was present was there was a disulfide bond between these two polypeptides, and the addition of the beta-mercaptoethanol and the dithiothriotol broke that, in which case we had two different polypeptides. Okay, so what we're doing in comparison between native page and SDS page is we're able to see a dimer, question mark, was there a dimer present? And what I'd like to draw, or a dimer, and I'm going to say multimer, question mark. Now, what I'd like to draw your attention to is this well right here, this lane right here, KOD. Okay, I'm first going to highlight it in my native page gel. Okay, now KOD, what we see is one band right here. We can use as a reference our molecular weight standards, which are labeled right here. This one is 480 kilodaltons, 146, and 66 kilodaltons. So this protein that I've highlighted right here, this KOD, well, it's definitely more than 66 and it's less than 146. It's closer to the 66 than it is 146. It's a log relationship on migration distance and molecular weight. So I'm going to call this about 95 kilodaltons. So we've got a 95 kilodalton protein, roughly. Now, it's native page, so we're dealing with the shape. We're dealing with the charge to mass ratio. So can we conclusively say that protein is 95 kilodaltons? It's a little iffy. I would say you can feel comfortable that it's, plus or minus 20%. But again, the shape and the mass to charge ratio is what matters. Now let's look at in this lane right here, KOD in the SDS page. What do we see? I see a band there. I see a band below that. And then I think I even see a third band there. I'm not 100% sure on that. There might be. I'm going to label these 1, 2, and 3. I get good separation between the bands number 1 and number 2. Between 2 and this potential 3, not particularly good resolution. So I would, one way to resolve that would be you could use a higher percentage gel to see if there is that third band there. But that's a little bit of a deviation. Okay, so protein 1, protein 2, and protein 3. What are the sizes of these? Okay, let's look over to our molecular weight ladder. 80, 60, 40, 30. All three of these are less than 40 kilodaltons because 40, so they are all less than 40 kilodaltons. So maybe this one's 38. This one's 36 kilodaltons, and I'm talking about the molecular weight, the molecular mass of these proteins, and maybe this one's 35.5. Well, if I added those up, that would be 90, 104, 109, 109.5. Approximately 109.5 kilodaltons for the overall size of that protein. Now, is that a reasonable number by comparison? Yeah, that is, because my structure right here was about 95 kilodaltons. These three combine to be about 109 kilodaltons. And it's a little high, but again, I need more resolution, and I'm dealing with a native page there, so my numbers could be distorted a little bit. So what this tells me, what this comparison tells me, is KOD, as an example, is a quaternary structured protein. It's a protein that is, well, multiple subunits folded together. And I only know that because I did my SDS page as a follow-up to my native page. Well, I hope this is helpful, and that'll do it.